Hello guys, in this lecture we're gonna talk about Euler angles, and so now we know that if you have a rotation matrix, basically we have 9 different parameters inside the rotation matrix. And it turned out that instead of having 9 different values, what we can have is we can have only 3 parameters to actually define that rotation matrix. And these 3 parameters can be the Euler angles. So there are different ways for doing this, the Euler angle. One conventional method would be to use a ZYZ Euler angle. And ultimately you'll have this phi, theta, and psi, basically. So we can choose, any ordering that we actually want to actually do that. And what that really means is that if you said ZYZ, basically you will start by doing rotation about the Z-axis, then about the Y-axis, and then about the Z-axis or the updated Z-axis. So after you have done the initial rotation about the Z, right, your Y will change, and you hit about Y, then your final angle is going to be rotation about Z. So if you do that, you will see that this is a rotation. And so we know this is a rotation about Z. We have a 1 here. Then we have a rotation about Y, which is this guy. Then you do rotation about Z again. And if you do this in multiplication, you will end up with this rotation matrix. And sometimes we have some arbitrary rotation matrix, like this guy here, right? I'll give you R between 2 frames. You put it in MATLAB, and then you're going to see numbers. If I tell you, find me the Euler angles that would correspond to this rotation matrix, what you will do is you're going to compare this rotation matrix to this guy. And this guy is based on ZYZ. So I could give you some other types, right? And then you would have to do the multiplication, get it, and compare it. And what you will do is you're going to start with the cosine theta. You will always, as a result of this operation, you will always have a cosine theta in one of the entries. So sometimes it's here, sometimes it is here in this example, we're doing the ZYZ Euler angles. So this is my cosine theta, and I'm going to compare this cosine theta with R33. So I know that cosine theta, or I can find theta, which is the inverse cosine of R33, or you can do it based on the tangent. And if you have a cosine theta, you'll have 2 solutions, so it's plus and minus. So in this case, we're using the A tan 2, which will also return plus and minus. So this is my theta. We can find it from here. And then if I want to find my phi angle, so just divide this guy over this guy, sine theta will cancel out. You can basically obtain A tan 2, which is R23. This is the Y component, sine over cosine, so R23. And my X component is R13. So you can find that. And then because it has a solution, we know it will be basically plus pi. And then finally, this is my psi angle. So you can find this from here, right? So if you divide this guy over this guy, you will eliminate sine theta, and it will be A tan 2 of this R32 over R31, which is this one. All right, so this is how, if I give you any rotation matrix and I ask you to find, what would be the corresponding Euler angles for that rotation matrix, you will basically result with these angles. Okay, next, so one last thing regarding Euler angles. Turned out that Euler angles, they don't actually do a good job to tell you the distance between 2 orientations. So if I have two different orientations, like frame 1 and then frame 2, and frame 2 is rotated by some angles. If I want to define that rotation matrix between these 2 planes, right? So we already know what that is. So it would be x1 and 0, y1 and 0, and then z1 and 0. And I can represent that by 3 angles. And it turned out that these 3 angles, if they were Euler angles, they don't really, they aren't. There's no exact mapping that this will always tell you the distance between these 2 orientations. So here's an example. So if I give you Euler angles 0, 90, 0, right? This is my first rotation transformation, and then this is another one, 90, 89, 90. So here you will see, okay, my other angles are this guy is 0, this guy is 90, this guy is 90, 89, this guy is 0, 90. You think that there is a big difference between, or these two other angles represent two different orientations that are, very far from each other. In fact, they are actually only 1 degree apart. So this, the first rotation here is giving you a mapping between, the base frame and then one frame, right? And then a second rotation is the same base frame but another frame, but these two frames are actually very close to each other, that are only 1 degree apart. Okay, what you need to know here is really, if I give you a rotation matrix, you should just tell me those 3 Euler angles. This is a goal. This one here. So there is another way of actually doing that, which is based on axis angle. So one way, we can take a rotation matrix now. We can find its Euler angles. Now, another way of expressing rotations or orientations is we can look into axis angle. And it turned out that I can also provide an axis, right? My axis K, and I will do basically, right-hand rule rotation about this axis. And this will actually correspond to another rotation matrix. And the way it works is that if I give you, this is my orientation vector, right, which is K, Kx, Ky, and Kz are going to be the coordinates of that vector, right? So you have, the x component of this vector, the y component, and then the z component. So now you basically have an arrow in space, and the rotation is being done about an arrow in space. The magnitude of this rotation is actually equal to the magnitude of this vector. So square root of kx squared plus ky squared plus kz squared is the angle, basically theta, the overall rotation that is done about this vector k. This is what you basically need to know here. And here is one last thing here. So if I give you a rotation matrix R, right? So you have some, various transformations, H03, for example. You can pull up your R rotation matrix from the first, 3 by 3 of that. And if I give you R, if I ask you to find K and theta, so before I ask you to find the Euler angles, now I want to ask you to find K and theta. How would you do that? So you first begin by finding theta. Theta is going to be actually equal to this. So cosine inverse, the trace of this rotation matrix R minus 1 over 2. So this is going to be my theta. What is the trace? The trace is actually simply sum the diagonal of that rotation matrix, which is basically simply R1 plus R2 plus R3. All right, so this is going to be the trace of that matrix. So now you find theta. The next thing is you want to find K. How do you find K? Just apply this equation. So you already find theta. So K is going to be equal to 1 over sine theta, R32 minus R23. So just by comparison, basically, you can find your K. So this is how you can find a vector and an angle that will correspond to a particular rotation matrix. One last thing, so if I give you K and theta, and then I ask you to find R, right? So before I gave you a rotation matrix, now I ask you to find, what is corresponding axis angle vector and then its angle theta. If you want to do this, forward mapping from K and theta to find R, here's how you do it. So simply R is going to be given to you as I, which is 1, 1, 1, plus S of K, which is basically the skew symmetric matrix. So S is actually given to you by this, and KZ, KY, KX basically are the coordinate or the coordinate of this vector K. So you have the vector K, you can find the matrix of skew symmetric matrix that will correspond to this vector K, simply multiplied by theta, then plus the skew symmetric matrix square, so this guy squared, multiplied by 1 minus cosine theta. All right, so if I give you this, then you will be able to find the rotation matrix, which would correspond to this particular value of K and this particular value of theta, right? And ultimately, that rotation matrix is simply defining the relative rotation of these two frames, right? So you have an initial frame, right? Then you have the vector K, and then you rotate it by theta. So let me draw that for you guys here. So here, what we're saying is that we have some base frame. X 0, Y 0, and then Z 0. And now I'm imposing some rotation by a vector K, right? So this is my vector K, and I'm rotating by theta, right? So I'm taking this whole thing and then I'm rotating it by that. So X0 is going to be here, Y0 is going to be there. So this guy is going to be my X1. This guy may be my Y1, and then this guy is going to be my Z1. Does that make sense? So as a result of this K, I'm rotating my base frame into my new coordinate, which is X1, Y1, and then Z1, right? And that rotation is going to be equal to I plus skew symmetric matrix K multiplied by sine theta plus S of K square. So just do, matrix multiplication. So basically square up that matrix multiplied by 1 minus cosine theta. All right. And this R will contain what? So this R is going to contain my X1 in frame 0, my 1 in frame 0, and then my Z1 in frame 0. Pretty simple. All right. So here, if I do this rotation about this vector by theta, basically, I'm going to find my X1. And not only that, I'm going to basically find the coordinate of my X1 vector in frame 0, coordinate of Y1 in frame 0, and Z1 in frame 0. This multiplication is also pretty straightforward. Okay, guys. So this is, heavily used in robotics, for, orientation, manipulation, etc. You can use this to be able to kind of rotate your tool about some particular vector, and you'll find that to be very helpful. One last thing here, that if I give you the angle, the x angle K and theta, to calculate the corresponding, so this is another way of doing what I just calculated, right? So we could use this, or, you can use this, ready to use. So based on theta, based on your R, basically. So this is basically the whole solution of what I just wrote earlier. So if you do this operation, you end up with this rotation matrix where Ux, Uy, and then Uz are the component of your rotation, of your vector vector axis, basically, about which you are making the rotation. Theta is your angle about which you are rotating. And then it's your, so you can just plug that in. So that is really what I wanted to cover in terms of, rotations. If you have a given rotation, how do you find its corresponding Euler angles, right? And if you have a particular axis, right, how do you find the rotation mapping? And how do you basically find the Euler angles, right? So, and that is really it regarding this chapter. Next, we're going to start now talking about robot dynamics or inverse dynamics.